last class we were discussing addition of angular momenta, and we had worked out certain examples where J1 is half and J2 is half, also J1 is 1 and J2 is half. In this class I will continue working out a specific problem in addition of angular momenta, and that is J1 is 1 and J2 is 1. This has some very interesting consequences and certainly helps one understand subtleties related to addition of angular momentum and the Klebsch-Gordon coefficients. So, with work with addition of angular momenta, so I have J1 is 1 and J2 is 1. So, these are two spin 1 objects or isospin 1 objects. So, if J1 is 1, the various uncoupled states corresponding to this are 1 1, 1 0 and 1 minus 1. Similarly, for J2 equals 1, I have the states 1 1, 1 0 and 1 minus 1, where the first index is J1 and the second is M1 here. The first index is J2 and the second is M2 there. M2 takes values minus J2 to plus J2 in steps of 1, similarly M1. So, the uncoupled basis states would be 1 1 with 1 1, 1 1 with 1 0, by with I mean direct product states. So, the uncoupled basis states would be of the form and so on, such states. Of course, using my notation I represent that as J1 M1, J2 M2, and therefore, this state for instance would just be 1 1 1 1. I wish to take a very specific example. In this case I would like to talk about an isospin 1 object coupling with another isospin 1 object. As I have said earlier, the pions form an isotriplet. There are 3 pions, 2 of them with the charges plus E and minus E and the other with charge 0. It is a neutral pion, these are the charged pions, and these have isospin and Iz values 1 1, 1 0 and 1 minus 1 respectively. So, this forms an isotriplet, and as I have mentioned earlier, every particle is defined by a state which is labeled by a set of quantum numbers, and certainly I and Iz are 2 such quantum numbers which label the state of the particle apart from charge, spin, rest mass and so on. So, this is an isotriplet, that means I is 1 and Iz is analogous to M, I itself is analogous to J that I have written there, and Iz takes values plus I to minus I in steps of 1. And that is how I have these 3 distinct states of pions. These are bosons, they have got spin 0 in units of H cross. Now, I would like to look at this problem as a coupling of 2 pions. So, 2 I equals 1 objects couple. So, I write I1 is 1, I2 is 1 and 2 isospin 1 objects or 2 isotriplets, in this case specifically 2 pions couple, and we want to look at the coupled basis and write the coupled states in terms of the uncoupled basis states as a superposition of uncoupled basis states, and therefore having a lot of Klebsch-Gordon coefficients arising in the process. So, I have the 2 pion system coupling of isospins. So I have I1 equals 1, I2 equals 1, which means I have the state 1 comma 1, which is the pi plus, 1 comma 0, which is the pi naught, and 1 comma minus 1, which is the pi minus. As I said earlier, just have to replace j by I and m by iz, and the entire angular momentum machinery follows as such. So the coupled state has I and iz. This is I1z in my notation, this is I1, this is I1z, perhaps I2, I2z, and so on. This could well be I2, I2z as well. So the coupled state has I and iz. I itself takes values I1 plus I2 to modulus of I1 minus I2 in steps of 1. And for a given value of I, iz takes values minus I to plus I in steps of 1, and that is 2I plus 1 values. So now let us look at the various coupled states in the 2-pion system. So that gives me I1 plus I2 to I1 minus I2 in steps of 1, and because it is a coupled state, I denote it by double braces. As a matter of notation, I have 2 lines out here. So I have the following coupled states: 2 2, 2 1, 2 0, 2 minus 1, and 2 minus 2. Similarly, if I is 1, I have 1 1, 1 0, and 1 minus 1. The second entry is iz. So we are now discussing the coupled state. This is the total isospin, the net isospin of the coupled system of 2 pions, and this is the net iz value. And it is good to remember that iz is I1z plus I2z. That means take the iz values of the first pion, the iz value of the second pion, add them up like you would to scalars, and you get iz. Then of course I have 0 0. So these are the complete list of coupled states that I can have when I combine 2 pions. My aim is to write the coupled states in terms of the uncoupled basis. So let me start with the coupled state 2 comma 2. Our aim, as I have said earlier, is to express this state in terms of the uncoupled basis. This is I and that is iz, the isospin of the coupled state, which we have got by combining 2 isotriplets, and this is the iz value. How could I have got this value for iz? This should have come from I1z plus I2z. So clearly the contribution has come from the uncoupled basis 1 comma 1 and another 1 comma 1. I have combined an I1 is 1, I1z is 1, with I2 is 1 and I2z is 1, and by scalar addition these two I1z and I2z add up to give me 2. There is no other possibility in this problem of getting a coupled state which has isospin 2 and iz2. Since this is the only state, the CG coefficient there is 1. That corresponds to the stretched case, where the iz value is the same as the I value. So that is an example of a stretched case, the CG coefficient being 1. Now in terms of pions, what would this state be? I1 is 1, I1z is 1. So this must be the pi plus, and that is another pi plus. So basically we have combined 2 positively charged pions to get this particular coupled state 2, 2. There is another stretched case as well, and that is 2, minus 2. On similar lines I can argue, and I can see that minus 2 can only arise from the uncoupled basis states 1, minus 1 and another 1, minus 1. This is I1, that's I1z, that's I2 and that's I2z. So minus 2 really came from minus 1 plus minus 1. Now in terms of particle content, this state with isospin 1 and the third component of isospin being minus 1 is the pi minus, and therefore I have this case 2, minus 2, CG coefficient 1, and that really came from the uncoupled basis states pi minus, pi minus. So this is another stretched case. So in a stretched case, the third component has the value I or minus I. In terms of our old notation, where we spoke of j and m, when m takes the value j or minus j, we call it a stretched case, and the CG coefficient is 1. So these are examples of stretched cases. But there are other states as well. For instance, there is the state 2, 1. After all, Iz can take values from plus I to minus I in steps of 1. So how do I get 2, 1? I can use an I minus on 2, 2. If I did that, I use the fact that the coefficient in this case would be root of I plus m times I minus m plus 1, m being Iz here. So I plus Iz times I minus Iz plus 1. So that gives me the state 2, 1, and on this side I have to work with I1 minus on this state, keeping this state fixed. In terms of particle content, the second entry is not changed. The first entry, the I1z value is brought down by 1, and therefore I go to pi 0, because pi 0 you will recall is a 1, 0. This is I1 and that's I1z now. And what is the coefficient? It is a 1 plus 1 times a 1 minus 1 plus 1. Now I work with an I2 minus on this state. Again, by the same argument, leaving the first entry untouched, I get that. In other words, I have 2, 1 is 1 by root 2 pi 0 pi plus pi plus pi 0. Look at the I3 values or Iz values. Here Iz is 1, pi naught has Iz 0 and pi plus has Iz 1, so they add up to give me 1. Similarly here, that's a matter that should be checked out at every stage, that the Iz values are all right. So let me remove this part of the algebra, and I can just write 2, 1 as 1 by root 2 pi 0 pi plus pi 0. I will comment on their symmetry properties a little later. So that is what we have. The next thing is 2, 0. Reduce the Iz value by 1. How do I get that? By using I minus on this state. What is the coefficient? It is an I plus Iz times I minus Iz plus 1. So, that gives me a root 6. And on this side, there is an overall factor 1 by root 2. I repeat the same kind of argument that I had earlier on. So, this object has I equals 1, Iz equals 0, and this object has I equals 1, Iz equals 1. This is I1, I1z, I2, I2z. So, apart from the factor 1 by root 2 outside, pi 0 goes to pi minus with an overall coefficient 1 plus 0 times 1 minus 0 plus 1. So, that is all I have here. Once more, this time pi 0 is unchanged, pi plus goes to pi 0. And what is the overall coefficient? 1 plus 1 times 1 minus 1 plus 1. So, that is root 2 again. The third term comes from here with pi plus going to pi 0, again pulling out a root 2 as earlier. The fourth term is a pi plus, pi minus, because pi 0 goes to pi minus, pulling out the coefficient root 2. So, the root 2's cancel out, and what do I have? I have 2 comma 0 is 1 by root 6 pi minus pi plus plus pi plus pi minus plus twice pi 0 pi 0. There is a pi 0 there and a pi 0 here. Let us mod square this. This gives me, between these two, I get a 2/6 and that is a 4/6. That gives me a total probability of 1. At every stage, one has to check that the mod square of the individual CG coefficients when summed over gives me 1. So, that is a half from here and a half from there. That gives me 1 and so on. So, how do I get 2 comma minus 1? That is the only thing that is left behind. I could have done that by using an I minus on 2 comma 0, but this involves 3 states. The algebra is a little bit more messy. So, instead let me start with 2 comma minus 2. Now, if I did that, I get an I plus acting on 2 comma minus 2 gives me 2 comma minus 1. What is the overall coefficient? It is root 4, because it is I minus m times I plus m plus 1. That is on the left hand side. On the right hand side, I use an I plus on this. So, the first pi minus goes to pi 0, leaving the second entry as such. The coefficient itself gives me a 1 plus 1 there. And then of course, again I have a root 2 pi minus pi 0. In other words, 2 comma minus 1 is 1 by root 2 pi 0 pi minus plus pi minus pi 0. Look at the I3 values. This is minus 1, that is a minus 1 plus 0, which is a minus 1. Here it is 0. This has I3 minus 1, that has I3 plus 1. So, term by term you can find that the I3 values match. So, indeed we have got all these states. Now, before we proceed, it is worth understanding two things. First of all, when we say pi 0 pi plus pi plus pi 0, as in the coupled state 2 comma 1, how do you distinguish between the two states? The particle content is the same, but basically when we say pi 0 pi plus, we mean that there are two beams of pions, and the pi 0 is from the first beam and the pi plus is from the second. Similarly, when we say pi plus pi 0, the pi plus is from the first beam and the pi 0 is from the second. So, this is the way we distinguish between the state pi 0 pi plus, with pi 0 as the first entry and pi plus as the second entry, in contrast to a state with pi plus as the first entry and pi 0 as the second entry. The same argument holds when we discuss the coupled state 2 comma 0, for instance, where we have pi minus pi plus pi plus pi minus plus 2 pi 0 pi 0. Now, the second remark is on the symmetry properties. In all these states, take for instance the stretched case 2 comma 2. If you interchange I1z with I2z, the state remains the same. In 2 comma 1, for instance, that amounts to interchanging pi 0 with pi plus. Such an interchange simply picks up an overall plus sign, and the state is symmetric under that interchange. Similarly, in the coupled state 2 comma minus 1, you interchange pi 0 with pi minus. Nothing changes. There is just an overall plus sign that is picked up. So, all these states with isospin 2 are symmetric under interchange of I1z and I2z. I will comment on this later. Now, let us look at the triplet state 1 comma 1, 1 comma 0, 1 comma minus 1. Now, 1 comma 1 is orthogonal to 2 comma 1. Of course, 1 comma 1 is also orthogonal to all the other coupled states, but here we are trying to fix the CG coefficients in the expansion of the coupled state 1 comma 1, and for this purpose we will only choose other coupled states with the same Iz value, that is Iz equals 1. So, and I know 2 comma 1. I know that 1 comma 1 is expanded in the following manner, similar to 2 comma 1. It will get a contribution from the state pi naught pi plus, also from the state pi plus pi naught. I wish to re-emphasize the fact that by this we mean pi naught from the first beam and pi plus from the second beam. By this we mean pi plus from the first beam and pi naught from the second beam. And if in your mind you imagine that these particles came with badges, white badges for this beam and black badges for that beam, then you know the difference. This comes from the first beam and this from the second. This comes from the first beam and that from the second. So, there is a definite difference, although the particle content is the same. There is one neutral pion and one positively charged pion. So, returning to 1 comma 1, I know that it should be a superposition of pi naught pi plus and pi plus pi naught. These are the only states that can contribute to 1 comma 1, but since I know 2 comma 1 to be the symmetric state 1 by root 2 pi naught pi plus 1 by root 2 pi plus pi naught, and I also know that a squared plus b squared is 1. So, I have a squared plus b squared is 1. We take the CG coefficients to be real without loss of generality. They will come with a phase otherwise, and we would write mod a squared plus mod b squared equals 1. Now, taking the CG coefficients to be real, I have this, and therefore, from the fact that 2 comma 1 is orthogonal to 1 comma 1, I have a by root 2 plus b by root 2 0, which implies that a is minus b. I need to use my convention now. So, I find that 2 comma 1, 1 comma 1 could be written as 1 by root 2 pi 0 pi plus minus 1 by root 2 pi plus pi 0, or minus 1 by root 2 pi 0 pi plus 1 by root 2 pi plus pi 0. Now, both would be all right. What is important is the relative negative sign, but I choose a convention and I use that convention The same convention throughout this problem. My convention is the following. Look at the second entry. This is a pi plus here and a pi 0 there. Pi 0 has an m value or iz value which is smaller than the iz value of the pi plus. So, the second entry has a smaller m value here, and I would use a plus there and a minus there, the same as this. That is simply a convention. Now, you could have gone ahead and put a plus here and a minus there, but you have to stick to that convention throughout the problem. So, this is 1 comma 1. Now, I need to get 1 comma 0. Notice that 1 comma 1 is an antisymmetric state. It is antisymmetric under interchange of the I1z and I2z values because this state has an overall negative sign and that has an overall positive sign here, and therefore, when I interchange pi naught with pi plus, which is the same as interchanging the iz values of the individual particles, I pick up an overall negative sign. So, this is antisymmetric on the interchange of the isospin labels. Now, if you look at 1 comma 0, there are two ways of getting this. Could have used an I minus on this, done it the way I got 2 comma 1 from 2 comma 2. I can do another way of doing this is by realizing that 1 comma 0 is orthogonal to 2 comma 0. Unfortunately, that cannot be used at this stage because it is also orthogonal to 0 comma 0, and since this is also unknown in the sense I do not know how to expand this in terms of the uncoupled basis yet, I cannot use the fact that this state is orthogonal to those two states and find the CG coefficients. I will be forced to use I minus. So, this is a point to note. I did not face this problem when I found out 1 comma 1 in terms of the uncoupled basis states, because there was exactly one state it was orthogonal to, and that was 2 comma 1. I knew 2 comma 1, therefore, I could get 1 comma 1. But here I just have to use I minus. So, when I do that, I pick up a coefficient root 2 1 0 is minus 1 by root 2. The pi 0 goes to pi minus, picking up a root 2, leaving the pi plus alone. Then the pi plus goes to pi 0 with an overall coefficient root 2, because that is a 1 plus 1. This I value is 1, the iz value is 1. So, it is root of 1 plus 1 times 1 minus 1 plus 1. So, there we are, but there is an overall minus 1 by root 2. Then the second term plus 1 by root 2. Similarly, pi plus goes to pi 0 with a root 2. The last term is pi 0 goes to pi minus with a root 2. Cancelling out the root 2's all over, I have 1 comma 0 is 1 by root 2. The neutral pions do not seem to contribute. I just have pi plus pi minus minus pi minus pi plus. This is an important point. It is important for the following reason, that if you told me that I need to form an I equals 1, iz equals 0 state from two isotriplets, I would expect a contribution to come from the I equals 1, iz equals 0, I equals 1, iz equals 0 combination as well, because I1z is 0, I2z is 0 and I is 0. But it turns out, once I work out the algebra in detail, it turns out the two neutral pions cannot be in the I equals 1, I3 equal, iz equals 0 coupled state. This is not just an accident. The fact that pi naught cannot exist in the coupled state I equals 1, iz equals 0 is really a statement of a very important symmetry in particle physics called Bose symmetry. I will get to that later. Right now, it is merely an observation. The details of the algebra show me that there is no contribution from two neutral pions to the 1, 0 state. So, let me list those states here in any case. So, I have 1, 1 is an antisymmetric state. It is 1 by root 2 pi plus pi naught minus pi naught pi plus. 1, 0 is another antisymmetric state that is here. It is 1 by root 2 pi plus pi minus pi minus pi plus. I need to get 1, minus 1. I can use the fact that this is orthogonal to 2, minus 1, and I know 2, minus 1. So, 2, minus 1, well, 1, minus 1 is also expandable in terms of pi naught pi minus plus pi minus pi naught. And 2, minus 1 is the symmetric state 1 by root 2 pi naught pi minus plus pi minus pi naught. I have a squared plus b squared equals 1 as always, and this gives me the fact that 2, minus 1 is orthogonal to 1, minus 1 gives me the second relation a equals minus b, which implies that if a is plus 1 by root 2, b is minus 1 by root 2 and vice versa. I use the convention that I used earlier. Look at the state, look at the second entry, that is my convention. Pi minus has an iz value which is less than pi naught. I put a plus sign here and a minus sign there. So, I choose a equals 1 by root 2 and b equals minus 1 by root 2. So, this is the working out of the thing. A is 1 by root 2 and b is minus 1 by root 2. So, there we are, that is 1, minus 1. So, we have the 3 I equals 1 state. Let me just put down all the states in one place. We are only left with 0, 0, which we will find shortly. The I equals 2 states are totally symmetric states, that is symmetric under interchange of the iz labels. So, that is a pi plus pi plus. Two, 1 is 1 by root 2 pi plus pi 0 plus pi 0 pi plus. Two, 0 had more contributions. This is 2, 1 out here. We got 2, minus 1. We need to get 2, 0 as well, and 2, 0 had many contributions to it. So, let me write that down. So, it had two neutral pions contributing to it. Two, minus 1 is simply 1 by root 2 pi 0 pi minus plus pi minus pi 0. 2, minus 2 was a stretch case. One, 1 was the antisymmetric case. So, let me just write that down. 1, 1 is out here. It is minus 1 by root 2 pi 0 pi plus 1 by root 2 pi plus pi 0. 1 comma 0 is 1 by root 2 pi plus pi minus pi minus pi plus. These are the two antisymmetric states. And 1 comma minus 1 is out there, it is 1 by root 2 pi 0 pi minus pi minus pi 0. I need to now find 0 comma 0, the coupled state 0 comma 0, the isosinglet state in terms of the uncoupled basis. I know that the contributions come from the same set of states that contributed to 2 comma 0 or 1 comma 0, in general 2 comma 0. Recall that 1 comma 0 did not have pi naught in it. So basically I can write this as A times pi plus pi minus plus B pi minus pi plus C pi naught. I have the following relations. I have 3 unknowns and I can determine them using the fact that A squared plus B squared plus C squared equals 1. That is the first thing. And then 0 0 is orthogonal to 2 0. So that gives me A by root 6 plus B by root 6 plus 2C by root 6 equals 0. So A plus B plus 2C equals 0. This came from the fact that 2 0 was orthogonal to 0 0. But 0 0 is also orthogonal to 1 0, and therefore I have A by root 2 minus B by root 2 equals 0. So A equals B or A minus B equals 0. This came from the fact that 1 comma 0 is orthogonal to 0 comma 0. So I have A equals B. So here I have 2A plus 2C equals 0, which implies that A equals B equals minus C. So I go back there and I have A squared plus B squared plus C squared equals 1, which implies that A is plus or minus 1 by root 3. Correspondingly, B is plus or minus 1 by root 3 and C is minus or plus 1 by root 3. I could choose any of this, but once more I follow the convention and I write 0 comma 0, the third entry C is pi 0. Of course, pi 0 has an isospin less than pi plus and more than pi minus. So I could choose any of these conventions and I have 1 by root 3 pi plus pi minus plus pi minus pi plus minus 1 by root 3 pi naught. This is again a symmetric state, symmetric under interchange of the third component of isospin term by term. So this is 0 comma 0. I have now listed out all the states that is a minus 1 by root 3 here. I have now listed out all the states and now we have the following comments, following observations to make. The first observation is this: the stretched case, that means 2 comma 2, 2 comma minus 2 and anything else in that multiplet turn out to be symmetric states under interchange of the isospin labels. Whatever I say for isospin also holds for any J1 and J2, but in this context we will be discussing a certain consequence. I have already mentioned it, the Bose symmetry. But now coming back to this set of states is symmetric under interchange of M1 and M2, or the third component of isospin in this context. We would like to prove this in general, that if the j comma j state, in this case the I comma I state, is symmetric under interchange of the labels. All the other states in that multiplet also satisfy the same symmetry property. Now if you look at this, again if you look at this state is antisymmetric under interchange of the third component labels, and all the other states in that multiplet are again antisymmetric. So I need to prove this in general. I need to show that in general you have a coupled state Jm. Let us start with a state which is symmetric, which is J1 M1. My J1 was equal to J2 because I am considering two I equals 1 states. So in this problem perhaps it would be more sensible to write I1, I1z, I1, I2z, and call this I and Iz. In general I would call this Jm for the coupled states, and this is like pi plus pi plus. So for instance it is J1 M1, it's the same J1 M2 because J1 equals J2. In my problem it is 1, and remember that M is equal to M1 plus M2. So when I use, so this is symmetric under interchange of M1 and M2, it is clear. So now I use J minus on this, it gives me root of J plus M times J minus M plus 1, apart from the H crosses which I have set equal to 1, J comma M minus 1. This is what I have on the left hand side. On the right hand side I have the first term gives me root of J1 plus M1 times J1 minus M1 plus 1, and the state itself becomes J1 M1 minus 1 J1 M2, that is the first term. The second time the operator acts on this, leaving this alone, so I have root of J1 plus M2 times J1 minus M2 plus 1. The first state stays put, the second one the M2 value changes by 1. So this is what I would have got. The original state was symmetric under interchange of M1 and M2. Now if you look at this state, again I see the same thing. If I interchange M1 with M2, this becomes J1 plus M2 times J1 minus M2 plus 1, J1 M2 minus 1, J1 M1. So you see this state becomes that, and that state becomes this, goes to this state goes to that, and that state goes to this with an overall plus sign. This is just an overall coefficient. So I can see that using J minus on a state which is symmetric is not going to change the symmetry properties of the state. So that is why if 2 comma 2 was symmetric, all the other states in the I equals 2 multiplet were also symmetric under interchange of the labels. Similarly, if I have a state which is antisymmetric under interchange of the labels, I would pick up the same antisymmetry property when I do a J minus on that state, and that is what we have in the 1 comma 1, 1 comma 0, 1 comma minus 1 series. So symmetry and antisymmetry properties are preserved under the action of J minus and J plus. We now go back to the observation that we made earlier, that two neutral pions do not contribute to the I equals 1, Iz equals 0 state. I am looking at this particular this one here, where I have expanded the coupled basis in terms of these uncoupled bases, and I wonder if there is a deeper symmetry which prevents a contribution from pi naught to this state, because certainly if M is 0, or if Iz is 0, I1z can be 0 and I2z can be 0, that is allowed. So at the face of it I would expect pi naught contribution here, the same way that there was a pi naught contribution to 2 comma 0 and also to 0 comma 0. out there. So, why is it that this is happening? This is happening for a very deep reason. It is called the generalized Bose symmetry. Pions are bosons. The statement is the following. For fermions there is an analogous statement, but I am now looking at bosons. The two neutral pions are identical bosons. They also happen to be isopartners, in the sense if you take a pi 0 and take its Iz value to minus Iz, nothing changes. It is its own partner. Pi naught goes to pi naught under Iz going to minus Iz, because the neutral pi naught has Iz equals 0. Whereas pi plus and pi minus are isopartners. When I take Iz equals 1 to minus 1, I get pi minus, and vice versa. So, pi plus pi minus are isopartners, and pi naught again they are isopartners. Pi naught is its own isopartner, if you know what I mean. So, you see the statement is this: if I have two identical bosons like pi naught, the total state in any case for a set of particles is going to carry a list of quantum numbers. Some quantum numbers related to space could be the space coordinates, then the spin quantum numbers, then the isospin quantum numbers, and so on. The total state of the particle, the pi naught system, or any two particles, we will look at this problem specifically, is made up of a space part which involves the space coordinates of the two particles, the spin labels S and Sz of the two particles, and the isospin labels of the two particles. Now, for two identical bosons, this is like if you go back to the harmonic oscillator problem, where I had two harmonic oscillators, the net state of the two-dimensional oscillator was given in my notation by ket Na direct producted with ket Nb, where Na was the quantum number corresponding to the first oscillator and Nb the quantum number corresponding to the second oscillator. So, these are different quantum numbers. There are some labels here, perhaps psi space in the case of the two pi naughts would be, psi space would be a function of r1 and r2, where r1 is the coordinate corresponding to the first pi naught and r2 to the second pi naught, and so on. Similarly, if you look at psi spin, it will have S of the first pi naught, Sz of the first pi naught, S of the second pi naught, and Sz value of the second pi naught. Isospin I1Z, I1 I1Z, I2 I2Z, as we have said in this problem. So, for two identical bosons, the net state or the coupled state is symmetric under pairwise interchange of the space and spin labels. So, if you look at pi naught, they are two identical bosons, and if you interchange the space and spin labels, the psi space psi spin, the net state which is psi space psi spin, picks up an overall positive sign. So, it is symmetric under pairwise interchange, goes to itself. Picks up an overall positive sign. Now, for isopartners, example pi plus pi minus, pi 0 and so on, the net state is symmetric under pairwise interchange of the space, spin and isospin labels. That means I1z and I2z. By this we mean I1z going to I2z and I2z going to I1z. By interchange of the spin labels we mean M1 going to M2 and M2 going to M1, where by M1 and M2 I mean the third component values of spin. In space would mean R1 going to R2 and R2 going to R1, where R1 and R2 are the coordinates of the two particles. The net wave function, the net state, is symmetric under pairwise interchange of all these labels, not one at a time, all of them, all these labels. So let us get back to pi 0, pi 0. The case of pi 0, pi 0, this is the generalized Bose symmetry or Bose principle. This is the Bose principle, Bose symmetry. We have already seen that since pi 0, pi 0 are identical bosons, under interchange of the space and spin labels, the net space spin part of its state does not change, just picks up an overall positive sign. But they also happen to be isopartners. Pi naught is its own isopartner. So now if you look at pi naught and use this, since psi space psi spin is already symmetric under interchange of the space spin labels, and the net state, which includes isospin as well, should be symmetric under interchange of all the labels. Just psi isospin alone should be symmetric under interchange of I1z and I2z, which means that the isospin coupled state cannot be antisymmetric under interchange of the two pi naughts. Look at 2 0 here, this is symmetric under interchange of the two pi naughts, there is no problem. Anyway, it would be symmetric under interchange of the two pi naughts because they are identical particles in any case, and therefore they cannot be present here. This is antisymmetric under interchange of the pi plus and pi minus, picks up an overall negative sign, but that is okay because these are not identical bosons, they are isopartner bosons, and between the isospin labels and the space spin labels I would expect the total state of pi plus pi minus to be symmetric. Whereas in the case of pi naught, already just the space spin part is symmetric, and therefore by the generalized Bose principle the isospin part alone should be symmetric under interchange of the two labels. Therefore it does not contribute to an antisymmetric isospin wave function. So there is a deep principle behind what we saw by brute force algebra, that 1, 0 surprisingly did not have a contribution from two neutral pions. The reason is Bose symmetry.